Can you see my screen already?
Yes, sir.
Beautiful. So what we want to discuss is a little bit about supremum and infimum, right?
Yes, sir.
But for us to be able to talk about that, okay, let me write what we want to do. So supremum and infimum. And in this case, we're just talking about supremum and infimum of sets, in real analysis. Because we could also have supremum and infimum of sequences and series. So for sets, it is still on the lower end of the spectrum. So supremum, so if you have a set A, before we can talk about supremum and infimum, we need to understand the concepts of lower bound and upper bound. So if you have a set A, an element is an upper bound if it is greater than or equal to everything inside A. Are you with me?
Yes, sir.
So if I have a set A, if I can get any element, when we are talking about lower bound, upper bound, supremum and infimum, we are talking about sets in relative to a bigger set. So for instance, we can start with saying let F be a field and A is a non-empty subset of F. So if I draw it, so sometimes things become clearer when you can draw pictures, and for sets and all of these things you can use Venn diagrams. So if this is F and this is A, or even to be more precise, we are dealing with real numbers, so I can actually use the number line. So if this is it's like a sub part of the number line, and this is F, and I now have a non-empty subset of that line. So if this is A, then everything from here to here is considered to be the upper bound of A. And everything from here, you can see that I'm including the endpoint, the boundary of A, the endpoint of A. So everything from here to here is considered to be the lower bound of A. So when a set has an upper bound, it is said to be bounded from above. When it has a lower bound, it is said to be bounded from below. And when it has both of them, it is said to be a bounded set. What I've said so far, is there any question? Do you understand?
Yes, I understand perfectly.
So the elements of A are maybe small letter A, all the things you can see here, small letter A. An element of F, let's call them small letter F. So if there is any F, if there exists any F in F such that F is greater than or equal to A for all A in A, then F is said
The upper bound.
to be an upper bound. So it is greater than or equal to. It can be strictly greater than, and it can be equal to, and that is why the endpoints of A are included. Similarly, if there so and and f tilde in f is a lower bound. It's a lower bound for a if f is less than or equal to a for all a in a. So the connectives and qualifiers that we use in writing our statements are very, very important. So when I say qualifiers, I'm talking about for all, such
Yeah.
that, all of these things that we are talking about. So for all a in a, it is important for us to have that. Okay.
Yes, sir.
So an upper bound or a lower bound for a set is not unique. Are you with me? Same
Yes,
thing
sir.
with lower bound. So we may have multiple upper bound. It is a set. That is what I'm trying to say. So that's why it is not just a point. You can see I use the pink color to show that. So this one is an upper bound. 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 And on the other end of the spectrum, this is a lower bound. This is a lower bound. This is a lower bound. So it is not unique. There can be many upper bounds and many lower bounds, but altogether it is a set, right?
Yes, sir.
And that is why we can talk about greatest lower bound
Yes,
and
sir.
least upper bound. So according to the name, the least upper bound, it is the smallest of all the f in f's that satisfies this property. Okay, so
Yes, sir.
all the f's on the right here, there are many of them, but the smallest of them, if it exists anyway, because it does not always exist, if we can talk about the smallest, it is not all the time that you can have the smallest element in a set, right?
Yes, sir.
For instance, this set does not have a smallest element. It does not have the biggest element. But this set has the biggest element. Can anybody tell me the biggest element of this one?
That's one.
The biggest element there is 1. It is the end point of the interval. Okay. But if I open it, we don't have the biggest element. Okay.
Yes,
But
sir.
can you tell me, can you give me one element in the upper bound of this set? So if this is our A, can you tell me one element in the upper bound of that set?
Still one.
1 is an element in the upper bound.
Yes, sir.
72 is an element in the upper bound. 1.5 is an element in the upper bound.
Yes,
What
sir.
about this other set B? Can you give me an element in the upper bound? Is 1 an element in the upper bound?
Yes, sir.
Yes, 1 is an element in the upper bound, even though it is in the set.
Yes, sir.
So that is to tell you that an upper bound can also be contained in the set that we are talking about. Okay?
Yes,
So,
sir.
but it is greater than or equal to all the elements of A, or in this case, or B. And the same thing with lower bounds. The lower bounds of A and B here, start from 0 downwards. Even though 0 is not in the set, we don't know the smallest element in the set. But when we are talking about least upper bound, so we are talking about the smallest of all the things that is in the set of upper bounds of a set. Okay, that is just the name, least upper bound. The least, the smallest. And the greatest lower bound, lower bound is on the left. So there's going to be one that will lead all of them. That is the greatest lower bound. And the one that is leading everybody here is the least upper bound. So the fancy name that we give least upper bound is what we call the supremum. And the fancy name that we give to the greatest lower bound is the infimum. So if you want to be formal about it, so let F be an ordered field. Why do we need order? We need order to be able to talk about something that is bigger, something that is smaller, right?
Yes, sir.
So we are talking about an F, which is an ordered field. So if we have F, an ordered field, F, an ordered field, and an A to be a non-empty subset of that ordered field. So it doesn't have to be a subfield, just a subset. So what is the supremum? So alpha is a supremum. I'm going to use red for supremum and blue for infimum. So alpha in F. So when we're talking about supremum and infimum, we are looking at elements in the the ambient space, the ambient set, not in the set A that we are talking about. So, but of course, we know that if it is in F, it could be in A, it could not be in A. So alpha in F is called the supremum, is called the supremum or the least upper bound of A if it satisfies two properties. So first and foremost, it has to be an upper bound, right?
Yes, sir.
So what does that mean? Technically, i.e., alpha is greater than or equal to A for all A in A.
Yeah.
Okay?
Yes,
It's
sir.
either you write it that like that, or you say A is less than or equal to alpha for all A in A. So that is one. Then the second property is that alpha is the smallest. I'm going to write it in in layman term first before we write it formally. Is the smallest element. So let me put a quotation mark. Smallest element in the upper bound or of the upper bounds. Or let me say smallest of the upper bounds. I think that is better. So technically, what does that mean? It means that if there is any other upper bound, so i.e., if alpha prime is another upper bound, then alpha prime must be greater than alpha or greater than or equal to. But because we have said another, I can use greater than. Okay?
Yes, sir.
There is a particular characterization of supremum too that we can talk about. So this one is a characterization that comes from the property. It is not always put in the definition, the characterization. So if alpha is a supremum, what happens if you subtract something from alpha? Where do you fall?
It is.
Where do you fall into if you subtract anything from alpha?
You fall back into the set.
You fall back into the set. So if for any okay, let me write it this way. Uh, okay. For any epsilon greater than 0, no matter how small, even if it is 0.0000001, for any epsilon greater than 0, there exists A in A such that A is greater than alpha minus epsilon. Do you understand that characterization?
Yes, sir.
So if you look at the diagram, so anytime you are doing analysis or anything, abstract math, try to, anchor it on a geometric thing that you can relate with. So if this is the alpha, the supremum, if we subtract epsilon from it, means we are going to the left. So we are saying if we subtract anything from, no matter how small we subtract, there is always something in the set that will be between that alpha minus epsilon and alpha. That is how to write it. Okay, so let me write it this way. So such that alpha minus epsilon is less than A and is less than alpha. Is it clear to all of you here?
Yes, sir.
Good. So let's do the same thing for infimum. So this is 1 for supremum. So for infimum, let me use beta for that. So beta in F is the infimum, is called the infimum of A, or the greatest of the lower bounds of A, if, again, satisfies two properties. Of course, beta must be a lower bound. Then what else? So what does it mean to be a lower bound? I.e., we have that beta is less than or equal to A for all A in A. So you can either write it like that or you say A is greater than or equal to B. Then secondly, beta is the biggest of
Down.
the lower bounds. So it is good to understand definitions because they are essentially what you are going to use to solve exercises, to prove statements. That is why I'm taking time to explain each component of the definition. So beta is the largest of the lower bounds. And so what does it mean technically? It means if beta prime is another lower bound, then we have that beta prime must be less than beta. So who can try to tell us what the characterization, the corresponding characterization would be for just like the one we did for upper bound and for supremum?
Okay,
Anybody?
let's see.
So if you look
That
at the
should
picture,
be
mm,
beta plus epsilon. Yeah, is
so good.
fine.
So for any epsilon greater than 0, no matter anytime we say for any given epsilon, they are saying no matter how small it is. So given any epsilon greater than 0, there is
Yes.
always an A in A.
We add to the
Exactly. Such that when anytime we add something to it, so we are going to have something like this. We will fall into the set. So there is always something between beta and beta plus epsilon. So it is, if you look at the picture, it means if I add, so if this is my beta, if I add something to it, I am going to the right. So there will always be an A in between beta and beta plus epsilon. So there is an A in between. Is that clear?
Yes, sir.
Beautiful. So we can now okay, common examples. So the set of natural numbers, does he have so when we are considering it which relative to at least let's say the integers, so does he have a lower bound?
Yes, sir.
It has a lower bound. Good. Can you
Yes,
give
sir.
me an element in the lower bound?
That's one.
One. So actually, we cannot use integers as the ambient space because we said want to use a field. So the least we can use there is the q, the rational numbers. Okay.
Yes,
Let's,
sir.
Yes, sir.
I have a question.
you have a question?
Yes, sir.
Okay.
In the statement that we made now and the first one,
Okay.
since both of them are falling back into the set normal, can't we use like for their first one, like less than or equal to for the first one, like the right answer for the first one, and the second one we are doing less, the beta is less than or equal to it.
Yes. So you have a very good point, and it is a correct one. So A can be less than or equal to alpha, and it can also be um, less than or equal to beta. That is correct. That is a good point. I was going to get there. But so what we are saying is if we add something or subtract something to the infimum or the supremum respectively, we are going to get back into the set. So if A is in the set and it can be equal at least if the supremum or the infimum they are already in the set, then it could be any of them because that is the property of the supremum or the infimum, greater than or equal to every element of the set. So that's a good point. Okay, good.
Yes,
Any
sir.
other question?
Yes, sir.
Good. So the set of natural numbers, when you compare it or when you embed it inside Q or R, for instance, it is bounded below, but it is not bounded above because both of them. So it's the picture you are going to be looking at is something like so you are going to have, so this is not going to be bounded. If this is our R, that is like this, then the set of natural numbers will now be something like this, where we start with one. Although it's still a very hot debate everywhere whether we start with zero or with one. So we are going it with one here. So it is bounded below, but not bounded above. But the set of integers, that one is also like this and like this. So it is neither bounded above nor below. Okay?
Yes, sir.
And the set A of 1 over n for natural numbers n, that one is bounded because natural numbers are bounded, of course. So the last one you can the smallest n you can have is 1, right?
Yes, sir.
Yeah.
So you can have 1 over 1. That's the largest number you can have. So it has a supremum of 1. It's bounded above by 1. And since its natural numbers go on ahead and on to infinity, okay, so it means it is bounded below by 0. You cannot get a negative number. So
Yeah.
it has an infimum of 0 and a supremum of 1. Okay, good. So with that, because uh, I don't want to spend too much time today, probably an hour or thereabout. So let us look at some exercises that we have here. So uh, there is 2.21 in the. Okay, so let me just go to the exercises instead of doing what you can read in the book already. So okay, so page 9, you have so theorem problem 2.2.35. The question says, uh, can I can I cut it and bring it here instead of rewriting it? I think I can. So let's have this. Uh, Save it, paste. Okay, so I have pasted it in Adam's inbox so that I can copy from there to the screen. Good. So we have this. So this is a question that we want to start with. Let A and B be non-empty subset of R which are bounded below. Okay. And let C be in R. Prove the following. So if C is greater than, so if C is positive, then CA is bounded below, and infimum of CA is C times infimum of A. So how do we start that? Proof. So we are dealing with A, set A. So we are told that A is bounded below. So what does it mean for A to be bounded below?
It means A has a lower bound.
Mute yourself,
Put the blame.
mute yourself, mute yourself. Good. So A has a lower bound. And so if A has a lower bound, we want to prove that so if A has a lower bound, by axiom of completeness, we know that there is an infimum. Okay, so we want to prove. So let S be that infimum of A. When there is a lower bound, there is an infimum, and when there is an upper bound, there is a supremum. I've forgotten whether that is axiom of choice or no, it's not axiom of choice. That's axiom of completeness, something like that. It's been a while. So let S be the infimum of A. So we want to see that CA is bounded below. So what does it mean? So we need to set our objectives. What do we need to show, or what do we need to see to confirm that CA is bounded below? We need at least one element that is less than or equal to all the elements of CA, right? So don't forget that CA is the set of C times A for all in such that A is in A. That is CA, right?
Yes, sir.
Good, good. So we want to look for an element that is less than every CA that we can think of. But because A is bounded below, there is an infimum. So we can say let S be the infimum of A. So if you want to be, totally safe, you can write why we know that there is an infimum. So since A is bounded below, there exists an infimum. So let S be that infimum. So what is the property of S? If S is an infimum of A?
That means it is the least. It is the least element in the set of A.
Not really. It may not even be in A.
Yeah, yeah,
So,
yeah.
so we say by definition, that means S is less than or equal to A for all A. This is why I was particular. I spent time with definition. So we are going to be making use of a lot of definition. So S is less than or that is the one of the first properties of infimum. So S is less than or equal to A for all elements in A. And because we want CA, okay, we can multiply both sides by C. But don't forget we have that C is greater than 0. So this implies that CS is less than or equal to CA for all A, or for all, yes, we can say for all A in A, or for all CA in CA, like this. Do you understand?
Yes, sir.
Good. So this first one is not really important, but this is the important one. For all CA in CA. So we know that the sign will not change because C is positive, right? If we
Yeah.
had multiplied by something that is negative, we know that the sign will be reversed.
Yes, sir.
Okay.
Yes, sir.
So
Yes, sir.
and what does that show? What does that show us? What does this line that we've just written? What does it mean? Can anybody see it? Let me clean this and put this like this. What does this line mean? We have something that is less than all elements of the set. So what does that mean?
I think,
What does that tell you about
what-
CS?
that means it is, I think something like about there's only one element there that is in A.
You're not saying what I'm saying. What does, okay, let's look at this first statement. Where did this first statement come from? It came from the fact that S is an infimum, right?
Yes, sir.
Yes, sir.
What type of element has this property? So CES is less than or equal to CA for all CA in this set. This is a set. This is an element. Just one, let's say a number. Okay, this is a number element. E is an element. So what kind of property did we define that looks like this? What is CS?
So that's infimum itself now.
Not just the infimum, and not yet the infimum. It is
Okay, greatest.
the only thing we know for certain about it, just from this line, is that CS is a lower bound. That is what it means to be a lower bound. That was what is defined to be a lower bound of this set CA.
Yes,
Okay,
yes, yes, yes.
let us go back to the definition of lower bound. What is a lower bound? Did I write it? Yes. So F is a lower bound for A if F tilde is less than or equal to A for all A in A. So we have an element that is less than all the elements in the set A. So in this case, our set is CA. And we have now seen an element that is less than all the elements of the set A, CA. So it means CS is definitely a lower bound. Is that clear?
Yes, sir.
Yes, sir.
Good. So where does that lead us? So we know something about S. We don't know something about CS yet. The only thing we know about CS is that it is a lower bound of CA. Good. So we need to show that it is the greatest lower bound. What else do we need to show? There are two things in the definition of greatest lower bound. This is the
Oh,
first one. One is that it is a lower bound, and the second thing is that it is the greatest of all the lower bound. Right? Are you guys with me?
Yes, sir.
with you,
Good.
sir.
So we have shown that it is a lower bound. I hope you understand why it is a lower bound of CA.
Yes, sir.
Good.
Yes,
So
sir.
good. So we want to anyway. This has already showed, giving us the first part of what we want to show. If we can get a lower bound, so we have finished the first part of the proof before we continue with the infimum part. So this, which implies that CA, small letter CA, is bounded below. That is the first part. So I'm going to the second part now. I want to show that the infimum of CA is C times infimum of A. So the fact that CA is bounded below, that implies that infimum of CA exists,
Oh,
right?
yes, sir.
That is how we actually started. So infimum of CA exists. But we want to show that that infimum is actually C times the infimum of A, C times S. The only thing we know about C times S now is that it is a lower bound. So to do, just like we do in chemistry, to do confirmatory tests that it is actually the greatest lower bound, we need to show that it is the greatest. How can we show that something is the greatest? We pick any other lower bound and show that it is definitely less than what we have. Okay,
Yes, sir.
so we
Yes,
want
sir.
we let me write what we need to show. We need to show, when anytime I write NTS, I mean need to show. If it is WTS, want to show. We need to show that for any other K in the lower bound
Why this?
of CA, for any other K in the lower bound of CA, K is less than or equal to CS. This is what we want to show. Okay, sometimes it is good to have a clear objective of what you want to do. So how do we show that? So if K is in the lower bound of CA, what does that mean? Okay, so
It means
suppose
K is
suppose K is a lower bound. So it should be small letters C and big A. So what does it mean?
it means K is less than or equal to C. That is.
K is less than or equal to CA for all A in A, right?
Yes, sir.
But we can divide both sides by C.
Sure.
So this implies that K over C, so for all CA in CA, so K over C is less than or equal to A for all A in A. Do you agree?
Yes, sir.
Yes, sir.
What does this line mean?
It means that we still have it means to have other bound greater than C.
It seems two of you are beside each other, so one of you should mute. So what does this line mean? If anytime you see this line, what does that tell you about K over C and A and capital A? We have written it like 4 times in this book already. Anytime you see this line,
I think what of it?
about K over C
K
and A.
over C is lower bound of A.
Exactly. So this implies that K over C is a lower bound of A, right?
Yes, sir.
Yes, sir.
But we know infimum of A exists. We know infimum of A. We know the greatest of lower bounds of A. Okay, so, but since S is the infimum of A, you know the meaning of infimum, the greatest of the lower bounds. It must be that K over C is less than or equal to S, right? Because
Yes, sir. Yes,
the
sir.
property of infimum is that it is greater than any lower bound that we can find. So since S is an infimum of A, and we're also saying that K over C is a lower bound of A, then K over C must be less than or equal to S. And if we cross, since C is we can always move C around in this inequality because we know that C is positive. So this implies that K is less than or equal to CS. And that is exactly what we said we wanted to show. So
Yeah.
that is exactly what we wanted to show. So K is less than or equal to CS, which means CS, because K was choosing to be arbitrary. You know, K is a lower bound of CA, an arbitrary choice. So this implies that CS is greater than or equal to, let me just write it in symbol, greater than or equal to any lower bound of A. So it is the greatest lower bound of A, which implies that CS, infimum of CA, is CS. What is S? S is infimum of A. I'm done for the first part. So he's just playing around. Infimum and supremum proofs just involve playing around with the definitions. Is there any part of this that is not clear before I go to the second one?
No, sir, but hold on. Let us take it through.
Okay.
It's okay, sir. Yeah. Yeah, no question, no problem.
All right. So Zach, is it clear?
Yes, sir.
Good. So the second part of the question says, oh, we now flip it. Let's do it together this time around. So if we flip it, we want to show that where is it? So if C is negative now, if C is negative, we want to show that CA is bounded above. And of course, when we are talking about being bounded above, that has to do with supremum. Supremum of CA is equal to C times infimum of A. So let's get to work. Again, like we started the last one, the only thing we are told is that A is bounded below, right? So
Yes, sir.
we cannot say anything about the supremum of A, but we know for sure there is an infimum. Okay? So
Yes, sir.
since A is bounded below, just like we wrote the other time, just rewriting it. Since A is bounded below, there exists an infimum of A. So let S be equals to infimum. Let S be equals to infimum of A. So let's write the property of the infimum of A as usual. So what does this statement, what is the first thing that this statement mean? Let S be equals to infimum of A. What does that tell us about S? The first thing it tells us.
This is good.
A question, sir. Since
Yeah,
it
About,
go ahead with your question.
is bounded above, are we not supposed to do like like supremum rather?
So
The second question is different.
it is A that is bounded below. We want to show, this is what we want to show. We want to show that CA is bounded above. We don't know anything about CA yet. Okay? So this one that we are, this first two lines is what we were given, from what we are given. We are given that A is bounded below. A bounded below, subset of R. So since A is bounded below, there exists infimum of A. And that means S is an infimum of A. Okay? So yes, so let me come back to what I asked. What does this mean? If S is an infimum of A, we have written it several times today. What's the first thing it means?
That means S is less than or equal to A.
For all, that to complete it, for all A.
Yeah, for all A.
A. So just like we did in the previous case, we need to multiply by C now. So I will do CS times CA. I want to write something. You tell me if I'm correct. Is this correct? Is this correct?
it is.
Considering this, it is not.
It's oh. It's, there
So
are
our C is negative.
yeah.
So the inequality sign will have to change. And that is
Yes.
where, okay, don't let me break the ice yet. So we can see that CS is greater than or equal to CA for all CA in CA. What does that mean?
Yes.
What does this mean?
It
It
means
means
CS
it
is
is
an upper bound of CA.
Beautiful. So we have already gotten the first thing we need to prove. So it means CS is an upper bound of CA. And once the upper bound of a set is not empty, what does that tell us? It tells us that CA is bounded above. So we have finished the first part. And once when it is bounded above, we know that there is going to be supremum,
Yeah.
right?
Yes, sir.
So which implies that the supremum exists. Supremum of CA exists. So what we want to show is that that supremum is equal to C times S, because S is our infimum of A. But of course, we have already shown the first part of the things that we need to show. Supremum of CA must be an upper bound. So CS is an upper bound. How do we now show the second part? So what is the idea? What do we need to show? What else do we need to show?
we take an element in CS in which it is
No,
greater than CA.
no. We need to show that if you take another upper bound, you need to show that I used K the other day, let's use K again. You need to show that for any upper bound K, what is the relationship between K and CS?
They are both upper bound.
Yes. What is now the relationship between them? If we want to show that CA is actually the supremum, what must we
That
show?
means
Greater than CA.
CA must be less than
Greater than CA.
CS rather.
CS must be less than K, less
Yeah,
than or equal to K.
exactly. So CS must be less than or equal to K. This is what we want to show. This is what it means for CS to be the least upper bound. We know that both CS and K are upper bounds now. So from here, we have said CS is an upper bound. Now we are saying K is another upper bound. For us to show that CS is the supremum, we have to show that CS is less than K, at least or equal to K. So how do we do that? Very simple. So we use the same trick we used before. We can see that what does it mean for K to be an upper bound? So since K is an upper bound of CA, what does that tell us about K?
K is included in CA.
Yes. But that's not what it means for K to be an upper bound of CA. What's the definition of upper bound of CA?
Yeah. Okay, it is greater than or equal to CA.
It is greater than or equal to C small a for all C small a in C big A.
Yeah.
So you have to be playing with definitions. Definition of upper bound, definition of lower bound, definition of supremum, definition of infimum. These are the things that you'll be using together. Then with properties of real numbers in terms of equalities, inequalities, translations, transitivity, and all of these things. These are the things you'll be putting together to generate, to construct a solid proof. So K is greater than or equal to CA. This is just definition of upper bound. Okay,
Yes, sir.
good. So we can, since we know something about A, we know it's infimum. I can divide both sides by C here. So if I divide both sides by C, what will happen? What is the inequality I'm going to get? Can somebody tell us?
Since we said
K
C
less-
is negative, I think to be less than equal to.
Good. So I'm going to have K over C is less than or equal to A for all A in A because C is negative.
Yeah.
And what does this mean? If K over C is less than or equal to A for all A in A, what does that mean?
It is
You
the upper bound of A.
is an upper
No, no. It is the what?
It is the supremum of A or something.
That's not what it means.
over over C is less than A.
It is not yet the infimum, or it is not the infimum, but it is what?
You go to the upper bound.
No. Come on, it is less than or equal to A for
Less
all
than
A
equal.
in.
It is the lower bound of A. The lower bound of A.
It is a lower bound. Don't say it is the lower bound. Like I told you, qualifiers and connectives are very important. You cannot say something is the lower bound. There is no the lower bound. When you use the, you are
Okay.
saying there is just one and a unique one. So there are
Okay.
many lower bounds. So it is only, you can only use the for infimum because when it exists, it is unique. You can only use D for the supremum because when it exists, it is unique. But when you say upper bound, it's a set. So in this case, because K over C is less than everything in A, it is, we know that it is a lower bound. So this implies that K over C is a lower bound of A, of set A. So what will be the relationship between K over C and S? If K over C is a lower bound of A, what will be the relationship between K over C and S? When S is the infimum.
That means both of them are lower bound.
Yes, but what's the relationship between them? They are both lower bound, but what's the relationship between them?
S is greater than KC or something. Over.
Exactly. That is what we want to see. Both of them are lower bound, but S is the infimum. And what's another name for infimum? The greatest of the lower bounds. If I want to cause fights now, I will say, what is the relationship between C. Ronaldo and Messi? Yeah. So, but you cannot say one is the greatest of all time over the other in that one. But
Yes.
we are
So
talking
I will say
about
it's good.
you don't have Messi stand. So maybe you have someone that will tackle you. Okay. But in this case, so if I now say okay, like Neymar now and let's say CR7, both of them
Ah,
they are senior men, they are senior players, they are upper bound players.
oh,
Okay. So I can say okay, let me use lower bounds. So Neymar and C Ronaldo, for instance, if both of them are lower bounds of players, of ancestral players, because C Ronaldo in that context is the greatest of his goals in that conversation, we will have that Neymar is less than or equal to C Ronaldo. In this case, K over C and S are both lower bounds, But because S is the infimum, it is the greatest of all the lower bounds. So we must have that K over C is less than or equal to S. Okay, why? Because S is the infimum of A, or greatest lower bounds, greatest of all the lower bounds of A. Right?
Yes, sir.
Yes, sir.
If I now multiply both sides by C, what inequality am I going to get?
K is greater than or equal to CS.
Exactly. K is
No,
greater
you see,
than or equal
no.
to C. Yes. C is negative. Anytime you multiply by negative, inequality changes because C is negative. And that is exactly what we said we wanted to show. We wanted to show that K is, K is greater than CS, or CS is less than or equal to K. These two things are the same thing. So that this confirms that CS is the what? Is the least of the upper bounds of CA. That is, the supremum of CA is equal to CS, but we said S is the infimum. That is C times infimum of A.
Uh,
So again, like I said, it's just playing around with the definitions and properties of real numbers. That is just what most of the things you do in this part. Getting familiar, very familiar with the definitions and playing around with the properties. So let's do one more before I wrap it up. So what's the next question that follows this? Let me check. Yeah, I can even open it here. Exact. Okay. Can you still see my screen? Can you still see my screen? You guys should mute yourself. So okay, I have muted him. Good. So the next one on the list here is all right. Oh, this nice one. Yes, it is important for us to do this because I think here we are going to need that characterization part. We have not used it so far, so let's use this one. Is keys tab now. There you go. Paste. Again, what are the hypotheses that we are dealing with? We are dealing with the fact that we know that A is bounded below, and B is bounded below as well. So using those two, we want to show two things. We want to show that A plus B is bounded below 1 and this identity 2. These are the two things we want to show. So let's start with the fact that A is bounded below. So what does A being bounded below mean? So it means that there is an infimum. So I don't know why there is feedback, but so I've muted you. So A and B are bounded below. So we know that infimum of A exists and infimum of B exists. But again, what is actually the set A plus B? The set A plus B is the set of all small a plus small b such that A is in A and B is in B. So what does it mean for infimum of A to exist? So let X be equal to A plus B be in A plus B. So to show that A plus B is bounded below, we need to at least figure out an element that is less than or equal to X, because X is just a random one chosen arbitrarily. But what do we know about small letter A and small letter B with respect to infimum of A and infimum of B? So because they are infimum, we know that A is less than or equal to infimum of A, and small b is less than. Oh, is that true? No. Is that statement true? What I've just written.
Yes, sir.
Eh?
Yes, sir.
Ah, A is in
Since
A.
A is an element, yeah, A is in A.
So can A be less than equal to infimum of A?
Infimum. Yes, now.
Ah, infimum is the one below. Supremum is the one above. This is
Yeah,
A
yeah,
here.
yeah.
Infimum is here.
Oh, it is greater than
Supremum
or equal
is
to infimum of A.
good. So I can rewrite it as infimum. So always remember the picture. This is A in A. Infimum is here. Supremum is here. Always remember that picture. So infimum
Yeah.
of A is less than or equal to A. And similarly, infimum of B is less than or equal to B. Those are definitions. And like I said, we are playing with definition and properties of real numbers. From the properties of real numbers, if we have these two things, I can add them together. So this implies that infimum of A plus infimum of B is less than or equal to A plus B. This is just property of real numbers. And A plus B is what? Is X. What does that tell us? It tells us that there is something that is less than or equal to, so let me rewrite it. Infimum of A plus infimum of B is less than or equal to X for all X in A plus B. What does that tell us about A plus B?
A plus B is like the supremum or something. Is it?
Mm-mm,
No,
mm-mm. A plus B is a
no,
set.
no, no.
So if
Yeah,
I
it's
I
just.
can write something like this, what does that tell us about A plus B?
It means A plus B is the set. and the infimum, these two infimum here, this infimum of A plus infimum of B, they're like the lower bound, like they fall in
If
the lower bound of A plus B
I
set.
can if I can get something, okay, it is true. This is a lower bound. Infimum of A plus infimum of B, not that individually, but their addition, infimum of A plus infimum of B, from what we have written now. Okay, let me write it out. Well, this implies that infimum of A plus infimum of B is a lower bound of A plus B. Does that make sense?
Yes, sir.
So what does that tell us about A plus B now? That tells us that what? A plus B is bounded below. That's what I wanted to hear. So if infimum of A plus infimum of B is a lower, there's something in the lower bound. That means that A plus B is bounded below. Right?
Yes, sir.
So if A plus B is bounded, that exists an infimum. Okay?
Yes, sir.
We, we, have, we have a candidate for the infimum, something that is in the lower bound. So we can see something here that is in the lower bound. Infimum of A plus infimum of B. It is a lower bound. So it is a candidate. We just need to confirm that it is actually the infimum. And this is where we need that characterization. Okay? So to show that infimum A or infimum
Sir,
of
sir, I have a
yeah,
question, sir.
okay.
This that line you underline, that infimum of A plus infimum of B is a lower bound of A plus B.
Yes,
Let's say it is the upper bound. That means A plus B is bounded above.
yes,
Is that it, sir?
yes. All right, sir. Good. So because we found that infimum of A plus B is less than or equal to all the elements in A plus B, then it means it is a lower bound. And if there is a lower bound, then it means A plus B is bounded below. And that guy that is in a lower bound is a candidate for infimum of A plus B. So to do a confirmatory test, we have to use, there are different methods. We have not used so far in this discussion, we have not used that characterization. Remember the characterization I wrote? Yeah, this one and this one. So because we are looking for the infimum, we want to use this characterization. So our beta now is this, infimum of A plus infimum of B. Our beta is infimum of A plus infimum of B. So to show that beta is actually the infimum, let me draw the picture so that sometimes pictures make it very clear. So if this is the set A, and we are saying this is the infimum here, the beta, the characteristic is that if we add an epsilon, no matter how small, if we add an epsilon, this is now beta plus epsilon,
It's all inside the A plus B.
it will fall. There will be an A. So we are going to have beta is less than or equal to A must be strictly less than beta plus epsilon. That's a property of infimum. So we want to see whether our beta here satisfies that property. So to show that infimum of this is equal to this, let's use the properties of infimum of A and infimum of B using the characterization. So since infimum So since infimum of A is an infimum, okay, of A, we know that for any for any epsilon greater than 0, okay, if we do infimum of A plus epsilon over 2, there will always be an element of A in between, right?
Yes, sir.
For some A epsilon in A. You will soon see why I'm using epsilon over 2, because I want to add them together. So, okay, this should be less than or equal to. Similarly, infimum of B is less than or equal to some particular beta, because it depends. I'm putting epsilon there because that A depends on the kind of epsilon we pick, how big the epsilon we pick is. So if a particular A works for this big epsilon that I've picked, if I pick a smaller epsilon, that A will not work. So we will need another A. So the A that we choose depends on the epsilon that we pick. So B epsilon is less than infimum. So this should be infimum of A plus. So infimum of B plus epsilon over 2 for some B epsilon in B. Right?
Yes, sir. Mm.
So this shows that if you now add these two together, what does that give us? That gives us infimum of A plus infimum of B, which is actually our beta in this case, is less than or equal to A epsilon plus B epsilon. And that will be strictly less than the sum of these two things, infimum of A plus epsilon over 2 plus infimum of B plus epsilon over 2. And that means that beta is less than or equal to X is less than or equal to beta plus epsilon. Okay, for so where beta, as we have written before, is infimum of A plus infimum of B, and X is A epsilon plus B epsilon, for that is an element in A plus B, and we are done. This is the characterization we want to see. We want to see that between beta and beta plus epsilon, there is one element in A plus B. So we have shown this is a property. So this implies for sure that beta is the infimum
I want to
of
hear that.
A.
Yeah, yeah. You can just tell him too. I think he'll be here. You can just tell him he'll be here for sure. I think it's just 5 minutes. I'll just stay. All right, sir. I have a question, sir. Sorry, sir.
Okay.
So my network wasn't good earlier, so I didn't hear it. But are we saying for that part of for any E or for any E greater than 0? So we are saying if you take any element and we divide it by 2 and we add it plus the infimum, you are saying it is greater than A or something.
So let me use the picture to explain again. This is A, okay?
Yes, sir.
And this is the infimum of A here. Is the greatest, the lower bounds are here.
Yes, sir.
We are saying if it is truly the infimum, if I pick any epsilon here means real number. If I add any real number to, to beta, I am
Yes, sir.
going, so if this is beta, beta plus epsilon will be here.
Yeah, yes, I know that.
So we have seen that there will be an A that is an epsilon in between beta and plus epsilon. That's what we are written here. Okay. So if it is true for epsilon, it is true for any division of epsilon. So it's true for epsilon over 2, epsilon over 3. Are you with me?
Yes, yes. Now the question is the epsilon. Like, is it like you are choosing the epsilon inside the set of A or any number?
So any number, it doesn't actually relate to A or B or anything. Any real epsilon here, and anywhere you see epsilon in real analysis is just a real number, a very small real number. Okay.
So
What
sir,
like what if the real number happens to be the first element in that A, and if you divide it, it is like actually like same to giving us that A back, that form of A back.
It's not possible. Okay.
Okay.
So that's okay. Maybe I don't get what you are saying. And that is why we have used less than or equal to here. So you know that beta is strictly less than beta plus anything, right? So far it is positive.
Yes, sir.
So, and anytime we have something that is strictly less like this, there is always a real number between them.
Yeah. Yes. Yes. Yes.
No matter how close they are, there is always a real number between them. That is the idea we are using here. So if we add anything to beta, whatever will be between them must be an element of A. And that is why we call it, because that thing will no longer be a lower bound. Because we are saying beta is the greatest of all the lower bounds. Okay?
Yes, sir.
So that's what the characterization is saying. So if we add anything to beta, we are going to have elements of A in between beta and beta plus epsilon. So whether epsilon or epsilon over 2 or epsilon over 10, no matter how small the thing you have added to beta, that interval will contain something that is not a lower bound, something that is in A. Okay? So for upper bounds, if I have an upper bound, this is my alpha. If I subtract any real number, no matter how small it is, so alpha minus epsilon is strictly less than alpha. And there will always be something in between them. So if alpha is truly the supremum, that thing must be something that is in A. So alpha minus epsilon is less than something that is in A that could be less than or equal to alpha. That thing cannot be greater than alpha if alpha is the supremum. So we are using that property here. We know that infimum of A is the infimum of A, so it satisfies that property. So if we add epsilon over 2 to infimum, there is an element of A in between the infimum of A and that sum. The same thing with B. Infimum of B and infimum of B plus something, there is an element of B in between them. This is the element of B in between them. And when we now add these two things together, it gives us infimum of A plus infimum of B less than or equal to A plus B, which is an element of capital A plus capital B, plus infimum of A plus infimum of B plus epsilon. So it means infimum of A plus infimum of B is actually the infimum of A plus B because it satisfies that characterization. Okay? Any other
Sir,
question?
like it seems like my network is not that good here again, so probably I'm still here, sir. I'm still here.
Okay. So what we have shown is we have shown that infimum of A plus infimum of B, which I denoted as beta, okay, satisfies the characterization of the infimum. It satisfies that when I add epsilon to beta, what I get is, there is always something in between beta and that sum that is an element of A plus B. So it means B is truly the infimum of A plus B. Only infimums have that property. If it is not the infimum, okay, if it's not the infimum, we would have something that was in the lower bound. Okay, so if we take another thing here and call it beta prime, and I add epsilon to it, so numbers that will be here, we could have a possibility that they are not in A. In this case, we are talking about A plus B. But if beta is the infimum, no matter how small of a real number we add to it, anything that we find in between beta and that new thing must definitely be A. And we have shown that what we can find in between them here is an element of A plus B. So that is why beta is truly the infimum of A plus B. So we are done. That means infimum of A plus B is equal to infimum of A plus infimum of B. So I'm going to stop there now so that I can attend to some other people. And I'll try to get a video recording of this session and post it and send the link to you guys. So if there are any other things from what we've discussed that you still need clarification on after going over the video again, you let me know and I'll see what we can do about it.
Okay, sir.
Thank you, sir. Thank you, sir.
Eshegun, sir.
Yeah, you're welcome.
Thank you, sir.
Right.
All right,
See
sir.
you.
Yes, sir.
Enjoy the rest of the weekend.
You too, sir.
Thank you, sir.